I have said for many, many years that before we discuss this theory of evolution, we need to discuss exactly what we're talking about because it has six different levels or meanings or stages. You'd have to, first of all, have cosmic evolution, the origin of time, space, matter. That has never been observed or proven or demonstrated. That is a religious belief.
Hello, everybody, and welcome to the next installment of An Astronomer Critiques Creation. Today, we're going to talk about the Big Bang, how it came to be a theory, and where it stands today. So, let's dive in.
The Big Bang is stupid. It didn't happen. It's dumb. It didn't happen. It's imagination. Okay.
And before we start in on a detailed discussion of the Big Bang, let's also mention a fallacy right up front. So, you'll notice in Kent's list of 6 stages of evolution, all of these mention the word origin of time, space, and matter, origin of chemicals, origin of life. The word evolution, even in the specific uh, uh, areas like cosmic evolution, stellar evolution, biological evolution, we would love to include the idea of where things come from, but we generally don't reserve the term evolution for that concept. The term evolution, um, for example, say stellar evolution, simply means once a star is formed, how does it change with time? And we can include the origin processes in that. Now we know how stars form, despite Kent saying we don't. That is going to be a detailed discussion for another video to also go along with the stellar evolution. I talked about how stars change over the course of their cycles. I didn't really detail how they form, but we do know how stars form. And so I'm going to make a detailed uh, response to that. But the point being that he wants to focus on this term origins. And in the video with Grayson, the debate with Grayson, he continually says, well, you don't know where the universe came from, so therefore your theory is incomplete. Um, that is another issue that I want to address further on in this, video. But for the moment, what I want to really hammer home at this point is that he continually focuses or equates, perhaps is a better phrasing, the word evolution with origins. And that's just not how we use it in most of the sciences. We can include the idea of origins, and in the realm of biological evolution, we would love to have a working model for how abiogenesis happened. We don't have it yet, and we freely admit that. Um, but that doesn't undo, not having that does not undo the mountain of evidence that we have for biological evolution. If you say, I'm going to define the idea of the theory of evolution to be, how have organisms changed once life existed? And the theory of evolution does a remarkable job of that. Again, I will defer you to other experts. But that's also the context that we're going to take in this video with the Big Bang. So just be aware of that. So the critiques we're going to be talking about today are coming from the debate that Kent Hovind had with Grayson Hawk on the Standing for Truth YouTube channel. And I'm actually gonna, this is more of the how we know what we know style that I did with the star formation, stellar evolution. And because I don't want to steal Grayson's thunder, I thought that overall Grayson did a really good job of responding to Kent's points. So this is not going to be a point by point going through and debunking everything that Kent said. This is going to be taking one specific point that Kent made and then going through the evidence and the process that we use to collect that evidence for the Big Bang and how we've come to understand what we know about the cosmos. And to preface this, I need to reiterate a couple of things that I've already said before in a few of the videos, but the Big Bang Theory is a theory, but that term has a very nebulous meaning amongst lay people. Okay, it's not often used exactly the same way that scientists use it. So let's reiterate that a theory, scientifically, is a collection of statements that can make predictions that you can then go test, right? That's the uh, basic idea of a theory. Um, and we've actually done that with the Big Bang. So the initial idea came from a basic set of principles, Einstein's equations, and it was realized that Einstein's equations allowed for expanding universe solutions. And then the natural implication was, well, if the universe was expanding, it had to be smaller in the past. And so, what were the conditions like in the past? And the first observational evidence came in 1929 with the discovery of the expansion of space-time from Edwin Hubble. We'll talk about that more in a little bit of depth here, but I just wanted to kind of set the stage for the tone of how this video is going to go. So what we're going to do is we're going to detail from the very beginning with Abe Georges Lemaitre and his calculations and the calculations of Friedman, um, the theoretical side that laid the foundation for the Big Bang, up through the observational evidences and then the subsequent predictions that came after those initial evidences for the expansion came in and people started to take the idea seriously, right? So this is not going to be a point by point rebuttal of things that Ken says. Um, there's a number of fairly ridiculous statements scientifically, and I think Grayson, holds his own here. So if you're interested in watching Grayson's rebuttals, um, I just highly encourage you to watch the entire debate. It'll be linked in the comments or in the description rather. But I would there are going to be a couple of points that I am going to make further on in the video. Um, but this is partially why debating people like Kent can be very exhausting. If you actually want to do a scientifically rigorous job, this video is going to turn into however long it turns into, and it's literally going to be rebutting the very first thing he said in the debate. So um, I'm not going to tackle the stellar evolution. I'm not going to tackle chemical evolution. I'm not going to tackle biological evolution. I'm not a biologist. I would not really feel comfortable tackling those issues. And other people have tackled it much better than I could anyway. So I will defer to those folks, people like Erica with Guts at Gibbon or Forrest Valkai with Reacteria. Um, but I just want to dive into some of the things that Grayson didn't have the time and perhaps the audience would not have necessarily understood or appreciated had he tried to take the time to go through some of the further evidences or the interpretations behind things like the angular power spectrum that he brought up. So I wanted to go through, just do a detailed outline of the Big Bang Theory, where it came from, and how we know what we know today, and That's it. So let's go.
Grayson, you're missing the first base. Where'd the energy come from? You don't have a good theory until you tell me you're saying we have energy. I agree, there's plenty of energy in the universe. That's what I told you. All the stars, all the energy from all the stars that have ever burned in all of history was in that dot. Do you believe all this energy from all these stars they're observing, red lines and green lines, was all that energy in a dot smaller than an atom initially?
Okay, so Kent wants to harp on the idea that you don't have a complete theory if we can't say where the energy came from. And this is a pretty common objection. Um, and to be fair, it is a good question. Okay, and it's one that we would love to answer, and hopefully we will have an answer one day. And if I were a betting person, I would say that eventually we will solve the problem. Um, but it is not a valid objection to say that you don't have a complete theory. Okay, so once again, a theory is a collection of statements that have predictive power. Now, there's one addendum that I will make to that, to what I said earlier, and that is that to really achieve the status of theory, the statement or collection of ideas already has to have some evidence behind it, right? So, just strictly speaking, a statement with predictive power is a hypothesis. Once that statement already has some evidential backing and continues to make predictions, then we can call it a theory. Okay. So that is why we call the Big Bang a theory, because it is a collection of statements that has evidential backing and also makes predictions. Okay. So let's dive in. Let's get into this. So the history of the Big Bang can really be traced back to the 19 teens, 1920s. So Einstein produces his general theory of relativity in the middle of the 19 teens, between 1915 and 1916. And the result of that theory was a set of equations. We call them Einstein's field equations. And immediately, various folks started to work with the equations and try and solve them for different situations. And out of these came the prediction of black holes from the Schwarzschild solution. Um, and on top of that, people started to apply the equations to the universe as a whole. And two people in particular that did this were Alexander Friedman, and he was able to show that the equations allowed for an expanding universe, a non static universe. And using more or less the same logic, a few years later, Abbe Gorgeous Le Maitre also obtains the same result, but he also makes the leap that says, well, if the universe is expanding, then it must have been smaller in the past, and also predicts the basic form of Hubble's law. Now, he wasn't able to predict the exact rate, but he did make a prediction that we should find Hubble's law, right? And so this is why Lemaitre, instead of Friedman, is named the father of the Big Bang. But um, we also do name some of the equations further down the road, and we'll discuss them after Friedman as well. So they both get a lot of credit for their work. But it really was Lemaitre's work that kind of set the tone for what we were about to find a few years later. And here is Lemaitre and Einstein. And it has to be stressed that Lemaitre's work was initially not well received by Albert. Um, Albert favored the steady state model of the universe, and so did a lot of other physicists. And the obvious implication being, if Lemaitre's model were true, then it would mean that the universe had a beginning. And it's not that this was necessarily an objection to, well, if the universe had a beginning, then religion is true. It was more, it was not as elegant scientifically. Um, there's a lot of problems that you have to solve once you assume the universe came from a smaller, hotter, denser state. What caused the universe to exist in the first place? And this is kind of what Kent is driving at, but you don't have to have that to have a complete theory. And a point that Grayson makes throughout the video is, take germ theory or atomic theory. You don't have to explain where atoms came from to explain spectral lines, to explain electron orbitals, to have quantum mechanics tell you where electrons ought to be. It would be nice to know where they all came from and have everything tied up in a nice little bow, but for the theory itself, it's not necessary. And the Big Bang is the same way. Although it is a problem that we would love to have the answer for, it's not detrimental to the theory because the theory of the Big Bang doesn't presuppose to know where the universe came from or what caused it. All the Big Bang Theory is concerned with is assuming the universe came from a hot, dense state in the past. What would the evolution of the universe, how would the universe change through time, and what observations can we make to support or refute that? Okay. Now, so again, Einstein was not in favor of this initially, but again, it was not on religious grounds. It was more um, Occam's razor, right? It's easier to assume the universe is eternal and static, and therefore that's why it seems to be isotropic, as opposed to having to explain the isotropic nature of the universe due to a very complex set of processes. So it really was more of a Occam's razor type issue for Albert. It wasn't necessarily a religious objection. But I should mention that Einstein was very gracious to Le Maitre after Hubble made his discovery of the expanding universe, and he initially called Le Maitre's work at a conference. He told Le Maitre personally, he said, "Your mathematics is beautiful, but your physics is abominable." I may have butchered the quote a little bit, but that's a good paraphrase. Um, but after Hubble demonstrated that the universe was indeed expanding, Einstein personally apologized to Lemaitre and was very gracious in that exchange. So, uh, you know, as new evidence comes in and it seems to be very solid, you incorporate that like a good Bayesian into your repertoire of knowledge. And Lemaitre's original paper, and part of the reason that it took a long time for Lemaitre's work to um, gain a lot of traction was because his original paper was written in French in a decently obscure journal. So not terribly many people were thinking about it or reading about it. But translated, the title says a homogeneous universe of constant mass and increasing radius accounting for the radial velocity of extragalactic nebulae. And this was published in 1927. And in 1929, we actually found the radial velocity of extragalactic nebulae. Now, at the time, this was still an open question. Galaxies were called nebulae, okay? And it was still a decently open question. And actually, Hubble's observations kind of really helped confirm this, that these were separate islands of stars, that galaxies were their own separate kind of thing and were not necessarily part of the Milky Way. So it was partially due to Hubble's observations that we kind of then moved galaxies into a classification of themselves, and we reserve the term nebula for gas clouds, if you will. But Edwin Hubble in 1929 does make this observation, right? So he observes the redshift of galaxies near the Milky Way and realizes that in general they are moving faster the further they are. So let's break this chart down just a little bit. The x-axis is in distance with megaparsecs. So a parsec turns out to be 3.26 light years. We won't go through the math to define exactly what a parsec is, but it turns out to be 3.2 light years. So megaparsecs, meaning million. So if you look at this kind of cluster of points right here, this would be um, 10 million megapar or 10 million parsecs, 10 megaparsecs. So that is roughly 32-ish million light years. Okay, so the Andromeda galaxy is roughly 2.5, 2.6 million light years away, give or take, plus or minus. And so these are, a little bit more than 10 times out. These would be almost 20 times out. And then you have the Virgo cluster right here. Okay. And the vertical axis is in redshift. And what this means is if you can measure spectral features from a spectrograph on specific targets from the laboratory, if you can identify that a line comes from a specific element like hydrogen, oxygen, or helium, or something like that, if you can identify the specific line, then from the laboratory we know what wavelength that line would be if measured at rest, if the object is at rest with respect to the detector. We do this all the time in introductory chemistry labs. But if those lines are shifted in wavelength, either toward longer wavelengths or shorter wavelengths, this is indicative that the object is moving. Longer wavelengths or redshift means they're moving away from you. Shorter wavelengths or blue shift means they're moving toward you. And so when you have a redshift, and by the way, this is linear. So the higher or the more distance along the spectrum between where you observe the line and where the line is in the lab, then that means the faster the velocity, the faster the relative motion. So this is what we call redshift. So suppose a line is right here on your spectrum and it's shifted to the red by some amount. That amount of shift indicates higher and higher velocities the larger the shift is. And so Edwin was able to use various spectral lines from galaxies and note that the further away they were, the higher their recession velocity from us was. Now, you have to have some sort of independent measurement to make the distance to the galaxies viable. And so, what he did was he used the period luminosity relationship of Cepheid variable stars, which had been calibrated a few years earlier by Henrietta Swan Leavitt, and that allowed him to estimate the distances. And so, having an independent method to measure the distances allowed Edwin Hubble to evaluate the recession velocities against those distances and noticed that more or less it was linear. And you have this cluster right here, which is noted as the Virgo cluster. And this is a nearby, relatively large cluster of galaxies. And the reason you have this kind of noise in the data here is because they are so gravitationally bound to each other that they're kind of swirling around each other a little bit. So you have some galaxies that are moving toward us, some that are moving away, and at slightly different rates due to their intense gravitational attraction. That gravitational attraction is also at work along with the overall expansion. So that's the source of these deviations from the Virgo cluster. They're random um, motions within the cluster due to their gravitational interaction on top of the stretching of space-time, right? But overall, this was fairly solid evidence, and subsequent features have been probed by telescopes like Hubble or the larger ground-based telescopes. And you can see in this chart that these distances are now probing, 20 times further out than Hubble did. And you'll note that, down here was the extent of Hubble's diagram, these blue dots that lie along the blue trend line. And when you can correct for those relative motions in the Virgo cluster, they fall right on the trend line of the recession velocity. And this is a fairly tight um, relationship the further out we go, out to 400 megaparsecs. So when we look out at, 20 times further than Hubble was able to look, we're now really starting to get at the deeper cosmic scales. And um, the relationship is just very, very tight. Now, one thing to note, okay, this is fairly interesting. We have the solid blue trend, which represents the overall, best fit trend of all the galaxies thus far. But you also have these dashed lines, 79 kilometers per second per megaparsec, and that comes from the axes, kilometers per second on the y-axis, megaparsecs on the x-axis. So your slope is going to be the units of your rise over your run. So the Hubble flow is measured in kilometers per second per megaparsec, right? Um, and there is currently a issue in cosmology known as the Hubble tension. And the Hubble tension is that Hubble's law, this idea that the universe is expanding, we name the slope of this line after Edwin Hubble and we name it Hubble's law. However, there are two ways to determine Hubble's law, one from observations like these directly from telescopes, and the other is from fitting routines with the cosmic microwave background. And we're going to talk extensively about the cosmic microwave background. But for the moment, the point being, both give slightly different answers. The observational with telescopes using the recession velocity seems to give values closer to 75 kilometers per second per megaparsec, whereas fitting with the cosmic microwave background seems to give 65 kilometers per second per megaparsec. And that might seem like, well, astronomers often, work within factors of 2 or 10 or whatever. So how's this a big deal? Well, the big deal is that the error bars on both are smaller than the width between them. So in other words, if this is 75 kilometers per second per megaparsec, here's 65, their error bars don't overlap. And so they can't both be right. And so this is a outstanding problem in cosmology, but it doesn't undo the, basics of the theory itself. Um, but it is an interesting problem, right? And interestingly, both sides are kind of convinced that they're right. So it'll take a few more observations to really determine things. But so far, JWST, James Webb Space Telescope, is coming down on the side that the Hubble Space Telescope did, which favors the telescopic observations. I should say the recession velocity observations. Um, but the cosmic microwave background groups are equally convinced that they are right as well. So it'll be interesting to see what happens over the next few years to resolve the Hubble tension. But the point being, okay, for the moment, now you have an idea, the Le Maitre paper that predicted an expanding universe, and now you have solid evidence for it. Another objection that a lot of creationists make is that they say, well, Le Maitre's prediction was actually retroactive because he republished his paper um, in 1931 in a British journal, the Monthly Notices of the Royal Astronomical Society. And so, because he's actually taking Hubble's data and retroactively making the prediction, therefore his original prediction is not as strong. The rebuttal to this is it still doesn't discount the fact that he wrote the original paper before Hubble's observations in 29. And the updated paper that he wrote was simply to bolster the fact that he'd written that original paper in 27 and to incorporate uh, newer observations from Hubble into his original idea. So, in that sense, you can say it was a retroactive prediction, parts of it, but the original idea that the universe should be expanding still holds as an original prediction that predates the observations. Right. And then, of course, today we have a very, very tight relationship, which is nearly irrefutable that the universe is indeed expanding. So, from that, we now have a set of formal predictions that physicists worked out once these observations from Hubble came in. And it took a little while, it took a couple decades. Um, not everybody was on board. There were still several proponents of the steady state model, but over the course of the, you know, 10 to 20 years, people were thinking about the Big Bang. It hadn't been coined the Big Bang yet. They were thinking about the expanding universe. But a couple of interesting predictions came out. So, Alpher and Herman in 1948 predicted that there should be leftover radiation from the initial state of the universe. And the reason being, if the universe was extremely hot and dense, then you should just have a soup of energy effectively, right? So you have really, really high temperatures. Whatever particles exist, they might be popping in and out of existence due to the extreme energies, and this is perfectly allowable by quantum mechanics. In fact, it's predicted by quantum mechanics. But as the universe expanded, those temperatures would necessarily have to drop. And once they dropped sufficiently low, then particles like protons and electrons, once formed, were stable. But it could still be hot enough that the atoms wouldn't form yet. So, in other words, protons could not reliably capture electrons to form stable hydrogen. Things were still just too hot. And you still have a lot of light bouncing around in here. So the basic model is that you have, all these photons, all these uh, light particles, if you will, scattering off of free electrons, and everything is just a big jumbled chaotic mess. But as the universe expands and it cools down even further, then you get stable hydrogen because electrons that pass close enough to a proton can form hydrogen. And as soon as you have that stable um, configuration and atoms starting to form, now all of a sudden light can pass much further without being scattered. And we know the temperature at which this occurs, roughly 3000 Kelvin. So once the universe was 3000 Kelvin in temperature, then the light that had been bouncing around and scattered in the early universe now had a free path, more or less, to just flow through space time. And so the universe should be bathed in this uniform radiation. And the radiation should therefore be a black body spectrum, and we'll talk a little bit more about what that means. But this is actually a very specific prediction, and this is why it's very important because they stated that the radiation ought to be black body, and then further they attempted to estimate what the temperature of this black body radiation ought to be based on what information they had at the time. And then on top of that, another paper, also with Alpher on it, um, predicted what the initial atomic compositions of the early universe ought to be. And basically, it is what you would think if you understand some basic atomic physics. Hydrogen being the easiest um, element to form, all you need are electrons being captured by protons. Okay, easy enough. But if you also have protons that haven't formed stable hydrogen yet colliding into each other, then they can also form helium. But it's much easier to attract an electron for a proton than it is for protons to collide exactly right to form helium. So you would expect the universe to be dominantly hydrogen, and then you would expect helium, and then absolutely trace amounts of lithium. And you don't really expect much more than that because there is a bit of a bottleneck that in that there are no elements with 5 nucleons or 8 nucleons. And so you can't just form higher elements from helium because helium has 4 nucleons, 2 protons, 2 neutrons. And the neutrons were formed in the process of the collisions with the protons. And so you wouldn't really get anything higher than lithium on average. If you do, it's absolutely trace amounts and only through very rare collisions where, uh, maybe 3 heliums collide all at the same time, 3 or 4, maybe you can get oxygen that way, but it would be absolutely rare compared to the total amount of hydrogen and subsequently helium. And on the rare occasion where a hydrogen atom combines with a helium atom to make lithium, okay. Um, Actually, really, it's more that 3 protons collide to make lithium. Um, it wouldn't be because of hydrogen colliding with helium. It would really be 3 individual protons. But you get a rough estimate for the basic composition of the early universe. And again, this is a pretty firm prediction. There is a humorous anecdote to this story. So this work was done by Alpher and Gamow. Gamow was also a very famous physicist um, for his work on cosmology, and he did do some work with Alpher and Herman on the initial prediction, but he wasn't on the paper with them, more correspondence. Um, but so Gamow noticed that there's a alliteration with Alpha and Gamma being very close to Alpha and Gamma. And so he humorously wrote in a colleague, Hans Bethe, um, onto the paper as an alliteration for Alpha, Beta, Gamma for the letters of the Greek alphabet. Alpha actually was not a fan of this move. He kind of resented that Beta was put on the paper without really significantly contributing to it, although he did do a number of significant contributions afterward as a result of being put on the paper. But I kind of, enjoy Gamow's sense of humor there, so I don't have a problem with it, but Alfred did, and that's definitely his prerogative. Um, but it is what it is. But so these are 2 very, very specific predictions that the Big Bang makes, and also need to pause at this point and maybe come back to this kind of overall picture of what we think the Big Bang looks like, or attempt to make a pictorial depiction of it. The Big Bang was not an explosion. Okay, we don't think of the Big Bang as an explosion, although any simulation that you type into YouTube, Big Bang simulation, is going to have an explosion in it. It's not really an explosion per se. It is simply the very rapid issue of space time coming into existence. So the Big Bang didn't happen anywhere, it happened everywhere. Let that sink in. The Big Bang didn't happen anywhere, it happened everywhere. And there's no central point from which everything is expanding, although kind of in this picture it looks like it. It's just a consequence of having to render, 3-dimensional and 4-dimensional concepts, space time, in 2 dimensions. But you can think of the surface of a balloon. If you blow up a balloon, everywhere on the surface of those balloon, or everywhere on the surface of that balloon, rather, is expanding if you're blowing it up, and there's really no central point on the surface of the balloon, and yet everywhere is expanding from everywhere else. So that's kind of the two-dimensional analogy we use. Now there certainly is a center of the balloon inside the balloon, but that is a third dimension. And so when you're talking about the surface of the balloon expanding, um, you would not perceive that third dimension if you were a two-dimensional creature on the surface. So likewise, there could be a center of the Big Bang in higher dimensions, but there wasn't a center of the Big Bang in the dimensions that we see or perceive. Okay, it simply is an expansion everywhere, all at once, uniformly. Okay, so um, here are Alpher and Herman, and their prediction of the uh, both nature and temperature of the cosmic microwave background 20, not quite 20, maybe 15 to 16 years later, it was confirmed by Penzias and Wilson, depicted here in the photo on the right, who were physicists working for Bell Labs. Now, they were ubiquitously not looking for the signature of the Big Bang. They were not looking for this cosmic microwave background. Um, but they were doing some antenna work for Bell Laboratories, and their instrument was tuned to the microwave region. And Alpher and Herman had essentially predicted that it should be in the microwave region. If you have black body radiation at 5 degrees Kelvin, that falls in the microwave range of the electromagnetic spectrum. And you would expect that your radiation would therefore be in the microwave range. Penzias and Wilson had no knowledge of this. They were not cosmologists. They were not tuned in to these ideas. They were simply, basically working as engineering physicists for a, commercial company trying to do some antenna work. And when they fired up their sensors with the antenna, they just noticed this constant background low level hum, and they couldn't get rid of it no matter what they did. And they tried everything they could think of. They cleaned the antenna horn, they cleaned the pigeon poop off of it, they cleaned pigeons out of it, they washed it down, they taped over rivets that they thought might be causing excess signal noise. So everything they could think of to mitigate the noise they did, but it still stayed there. Somewhat ironically, just down the road, a physicist and a graduate student were actually actively looking for the evidence of the Big Bang, but their instrument hadn't fired up yet when Penzias and Wilson uh, had fired up theirs. And Penzias and Wilson basically write this just very innocuous letter to the Astrophysical Journal, basically saying, yeah, we've detected some low level hum from everywhere in the sky. No matter where we point our antenna, we see it. And the it was Dickey and Peebles, I think it was, were the two that were actively looking for. And as soon as they heard about it, they said, "Oh man, we've been scooped." Um, and then they contacted Penzias and Wilson, and they did some collaboration work on it. But Penzias and Wilson ultimately won the Nobel Prize for their discovery, right? So once again, kind of reiterating, Alpher and Herman made a very specific prediction that this radiation should fall into the microwave portion of the electromagnetic spectrum, estimated its temperature. Now, Penzias and Wilson's temperature was cooler than what Alpher and Herman had initially predicted, but as we will see subsequently, not necessarily a huge deal. Um, but so now that the Big Bang had some very firm predictions and very firm evidence for it, the expansion of the Big Bang, a black body radiation in the microwave region of the spectrum, now people were forced to take the Big Bang as a theory very, very seriously. Um, but there were still some puzzles that remained. The universe seemed to be thermally uniform. Um, Over the next couple of decades, as astronomers were measuring different parts of the universe, they just couldn't find high temperature variations. Um, but if you look at one side of the universe, maybe 100, yeah, let's say 100 megaparsecs, um, the temperature of the universe seemed to match when you look 100 megaparsecs in the other direction. So, how would different regions of the universe, how would they have had time to communicate with each other? So, this was a major problem. Einstein's theory of general relativity is the quintessential theory that describes the curvature of space time due to gravity. However, on large scales, it doesn't seem to be curved in the way that the mathematics predicts or talks about. So, why is the universe not curved at the largest of scales? Perturbations early in the universe really should have caused large scale it should have caused large scale deviations from flatness down the line. So why didn't it? Why, even though we have galaxies and galaxy clusters, why does the universe seem to be what we call geometrically flat? And the Big Bang also should have had enough energy in the initial hot dense state to create a number of magnetic monopoles. To date, these monopoles have not been observed. So, where are they? Well, to solve that, and this is admittedly a slight ad hoc hypothesis, we had no reason to justify why it happened at the time, but it was suggested by Alan Guth in 1981 that perhaps the universe underwent a very brief and rapid rate of expansion in the first very, very, very small fraction of a second. It's debated exactly how long inflation occurred, but a round ballpark estimate would be to say, 10 to the negative 36 seconds. So in that time of 10 to the negative 36 seconds that the universe was expanding, um, it expanded by a factor of about 10 to the 36. So it went from basically the size of an atom to maybe the size of a cluster of galaxies in that very, very short time. And what that does is it basically smooths out the universe and any um, fluctuations, temperature or density fluctuations, and just basically makes them all smooth. It just smooths those fluctuations out, and it also dilutes the density of any magnetic monopoles so that they're essentially non-observable. And so inflation, although ad hoc at the time, it does solve the some of the problems that physicists recognize and cosmologists recognize with the Big Bang. Um, and even today, we still don't know. We don't have a causal explanation for inflation. But I will also discuss some of the evidence for inflation that we have, and therefore it is not anymore just an ad hoc idea, but seems to be an idea that has some evidence behind it, even if we can't explain where it came from, right? So, a little bit going back to black body radiation. Um, Black body radiation is radiation that is emitted from a source that is a perfect emitter and does not reflect. So, common examples of black body emitters, at least to very, very good approximations, are things like stars, minus their emission and absorption lines in their atmospheres. Stars are essentially a black body emitter. And the radiation in your oven, for example, is also a black body. So if you were to measure the intensity of the radiation in your oven, uh, at different wavelengths or frequencies, then you would find that it followed this basic pattern. So the pattern of black body spectrums is as follows. Wherever your intensity starts to rise rapidly, it will rise to a peak and then it will taper off with an exponential tail. Okay. And where you peak is directly correlated with your temperature. So if you have multiple objects and they're all at different temperatures, number one, the cooler peak will have a longer peak wavelength. So you'll notice that this 3000 Kelvin curve peaks at roughly 1 micrometer, whereas the 4000 Kelvin curve for an object at 4000 Kelvin, it peaks at maybe 0.7 micrometers. And an object at 5000 Kelvin peaks at about 6 micrometers. But you'll also note the intensity differences. Okay, so these three objects, 3000, 4000, 5000, will also vary in intensity very much. Your 5000 Kelvin object, if you're talking about all of these objects having the same radiative area, right? So think of like a ceramic disc, three identical ceramic discs, one heated to 3000, one heated to 4000, one heated to 5000. The 3000 Kelvin disk, even though that's really, really hot compared to, our everyday standards, that's almost 6000 Fahrenheit. It would be dim compared to the 5000 degree object. Or I really should say 5000 Kelvin object. We really don't use degrees in Kelvin. So your 5000 Kelvin object is going to glow with much more intensity than your object at 3000 is. But the basic idea is that a black body curve has this shape, right? It rises sharply, comes to a peak, and then exponentially tails off. And this is the equation that describes this curve. So this particular equation is written in terms of the wavelength, lambda, and h is Planck's constant, and k is Boltzmann's constant, and c is the speed of light. But if you have a black body, then it will follow this exact curve. Now, why is this important? Well, it's important because remember, Alpher and Herman predicted that this would necessarily be a black body. The cosmic microwave background would be a black body spectrum. In 1989, we launched the COBE satellite, the Cosmic Background Explorer, and one of its main functions was to investigate the nature of the radiation of the cosmic microwave background, and it returned this curve. Okay, so the red points are the COBE data, and the blue fit is a black body spectrum. By inserting this temperature, if you look at this peak wavelength right here, you can, this is in terms of frequency, but frequency and wavelength are inverses of each other. So if you convert this frequency into a wavelength, this peaks at roughly 6 centimeters, so 1/6 of a centimeter in wavelength, and put that into this equation, you would get this curve. And notice how perfectly it fits. So this prediction was stunningly confirmed. Now, they predicted 5 Kelvin. COBE measured 2.725 Kelvin. Is this a problem for the theory? We'll discuss that in more detail here in just a little bit, but it turns out no. I'll explain why, right? But the point being, this is a stunning confirmation that the curve is black body, and we can actually measure the temperature to stunning precision. So our current model of the Big Bang after the Kobe satellite was launched is basically you have the creation of the universe. It came into existence somehow, some way. It went through a very rapid rate of expansion, and about 375,000 years after it came into existence was when it hit that 3000 Kelvin limit that allowed free photons to pass through the universe without being scattered very often. And that is what we call the afterglow of the Big Bang. This is the cosmic microwave background. And then we have the dark ages. And so this is while matter was kind of clumping together that enabled it to form things like stars, galaxies, and so on. And then once you have that matter clumped enough, then you got the initial formations of stars, the initial seeds that formed galaxies, and then you have galactic and stellar evolution from that point since. Okay. So your stars started to form roughly 400 million years after the Big Bang. And so now we're in the era of, we've got 13.3 ish billion years of stellar and galactic evolution. Okay, so this is the current state of the Big Bang. One of the other predictions that the Big Bang makes is that, pardon me, the universe should be the same everywhere you look. And this is what we call isotropic. And in the late 1990s, the Hubble Space Telescope was used to look at one region of the universe for 10 days. And it was just a little tiny point near the Big Dipper. And it was a point that was largely devoid of foreground stars. And it just stared at this region of the sky. And this is what it turned into. Okay, so this is what's known as the Hubble Deep Field. And we do have a couple of foreground stars. You can tell foreground stars from galaxies because they have spikes. So here's an object with some spikes, here's some spikes, here's some spikes. But effectively, everything that doesn't have that spike in it is a galaxy. And when you look at a picture like this, you just see galaxies everywhere. And you see galaxies in various stages of galactic evolution, but you see galaxies all over the place. And this really heavily leans toward the idea of isotropy, in that everywhere we look, we should see galaxies and we should see them at various stages of galactic evolution. Well, we do the same thing. We point the Hubble almost 180 degrees away from the original deep field, and we come up with what's known as the Hubble Deep Field South. And again, we pointed at a region that's largely devoid of stars. This is what we have, these few points here, here. But again, everything else that's not spiked is a galaxy. And you compare these two pictures, and you just see galaxies everywhere in various stages of evolution. So the isotropy of the universe seems to be solid observationally. A very, very key point, right? Then in the early 2000s, we launched what was known as the Wilkinson Microwave Anisotropy Probe, or the WMAP. And this is the probe that wanted to probe what anisotropies there were in the Big Bang, right? Or in the cosmic microwave background specifically, right? And so the picture on the right is a picture of temperatures in the cosmic microwave background. And yellow and red are where it's just ever so slightly hotter, and blue is where it's ever so slightly cooler. How much hotter and cooler are we talking about? The scales of these deviations are on the order of hundreds of microkelvin. So let's come back. I think it was this slide here. Yeah. So our temperature is 2.725 Kelvin. This is the place holder that would represent hundreds of microkelvin. Okay. So we're talking about deviations on the order of 0.00 something. Okay. So we're talking about a prediction 2.725 plus or minus 0.00 something. Okay. These deviations are extremely small compared to the overall average temperature of 2.725. The maximum deviations, in fact, are less than 0.25% of the average. That is stunning isotropy. But the fact that it is anisotropic at the level of hundreds of microkelvin is significant, as we will see. So, whoop, blank slide in there. What were the major results from WMAP? Well, WMAP measured the age of the universe to be 13.7 plus or minus 0.2 gigayears, and it also determined the angular power spectrum of the temperature fluctuations. Now, this is a piece of evidence that Grayson used throughout the debate, and I just don't think Ken had a sense of what Grayson was talking about with it. And to be fair, this is a fairly technical piece of evidence. Um, so I want to go into a little bit more depth of talking about where it came from, why it's used, how it matches, or why it has predictive power, and why it's a powerful tool for the theory, and go into a little bit of the math for how it's generated. Okay, so we want to step through um, these two pieces of evidence from WMAP and say why we know what we know from these. Okay, that's the goal that we're going to do in the next few minutes. First things first, the age of the universe. Okay, so as I mentioned before, Friedman gets credit for some of the equations in cosmology and Big Bang theory. And when he rearranged Einstein's field equations, he came up with this equation. We now call it the Friedman equation. R, the variable R here, is what's known as the scale factor. So this just basically tells us how large the universe is at different points in time. At the current epoch, our current time, we would say the scale factor is 1. The universe is as large as it is. So this is basically a way to measure how the size of the universe is changing with respect to time. That's what this drdt term is doing right here. G is Newton's gravitational constant, and then these rows, rho sub m, rho sub rel, and rho sub lambda, are the density parameters for different constituents of the universe. Rho sub m is the baryonic matter density. Rho sub rel is the relativistic material, so things like photons. And then lambda is the density of the dark energy that is causing the universe to expand. And not just expand, but accelerate in the expansion. And on the right-hand side, you have this negative kc squared. So k is a parameter that measures the curvature of space. So again, Einstein's equations relate the amount of energy and matter in the universe to its curvature. And so Friedman is basically relating the energy and the matter in the universe in terms of their densities to the curvature multiplied by the square of the speed of light. So the left-hand side is the total amount of stuff and how it's expanding and the rate at which it's doing so. And the right-hand side is the amount of curvature. Modern observations tell us that the curvature is flat. That correlates to a value of k equaling 0. So to our best estimates, the right-hand side of this equation is 0. Okay. Now, what we do is we typically use some dimensionless parameters, and so we don't really think of the densities themselves, but we think of them in terms of ratios of in relation to what we call the critical density. So rho sub c in these ratios, rho sub m to rho sub c, rho sub rel to rho sub c, or rho sub lambda to rho sub c, rho sub c is the critical density that the universe would have to have in order to be flat, in order for that k to be 0. And so we write these dimensionless density parameters, omega sub m, omega sub rel, and omega sub lambda, as the ratios of the mass, relativistic material, and dark energy densities to that critical density. And in normalized units, the critical density is just 1. And so basically, we're interested in what fraction of the overall density of the universe is due to matter, due to relativistic material, and due to dark energy. And this is where WMAP has made stunning progress because it is able to measure these parameters. It measured the baryonic mass to be about 0.27 or 27% of the universe. Relativistic matter is almost negligible compared to the baryonic matter and dark energy, but it is there at 8.24 times 10 to the negative 5, and the dark matter is coming in at 0.73. And so basically, our universe at the current moment is dominated by baryonic matter and dark energy. Okay, at least according to WMAP calculations. Now, I'm skipping the math to go from this first equation to this equation, but the idea is that if you rearrange the equation for the drdt term, you can then take the reciprocal and come up with an equation for dt-dr, and then multiply the dr up on the other side, and you can integrate. And this allows you to estimate the time. This gives you the age of the universe. Okay? So, by inserting the WMAP values for the density parameters into the integrated time equation, we can estimate what the age of the universe is, and it comes out to be 13.7 plus or minus 0.2 gigayears. So this result comes straight from the WMAP data, and its valuation of the density parameters of the universe. And this is the most reliable age that we have at the moment. One thing creationists really like to do is they like to say, well, years ago in the textbooks, the universe was 20 years old, and then it was 10 billion years old, and then it was 15, and now it's 13.2. It's changing all the time. That's true, but our error bars are getting smaller as well. If the WMAP age for the universe is incorrect, then all of cosmology is a stunning coincidence, right? It's possible, and we have to entertain the idea that we might be wrong, but it's a pretty stunning coincidence. So at the moment, cosmologists take this to be a true statement. The confidence interval is well within our ability to say, okay, it seems to be this, we're going to move on to the next interesting problem. And there's no shortage of them, to be sure. But we do have to entertain the idea that it might be wrong, but more than likely. And when we say more than likely, what we mean is far more than likely. If the age of the universe changes again, it will be within the context of the error bars here and not change significantly. If it changes by more than a factor of 2 or 3 outside of the error bars, that will be significant. But the evidence would have to overwhelm and subsume the WMAP evidence. And at the moment, the WMAP evidence is fairly solid. So for the moment, the best estimate for the age of the universe is 13.2 gigayears, or 13.2 billion years, plus or minus, or 13.7 rather, plus or minus, 200 million years. What's 200 million years amongst friends when you're talking about, billions? But yeah, this is a really, really solid um, estimate for the age. So to within the ability of WMAP to do calculations and do measurements, really for WMAP to do measurements and then for us to do the calculations with those measurements, this is as solid as it gets. It really is a stunning um, ability to get those error bars lower than 10%, right? It's actually lower than 20%. So um, I'm sorry, lower than 5%. So it really is quite stunning. So one of the other major things that the WMAP instrument contributed to is this power spectrum. And at this point, I'm going to pause and let Kent say a few words about it.
Classic example of what we call the snow job. Okay, let's throw out this chart and this data. Okay, you've shown a bunch of it's like 6,000 degrees Kelvin. Ooh, that's pretty hot. Okay.
All right. So I wish this is actually one of the points that I wish Grayson would have pushed back on a little bit more. Um, Kent 100% betrays that he just simply doesn't understand scientific literature. And on on the surface, it's forgivable if you're not used to reading scientific journals. These charts can be very opaque, even to professionals not in the field. They can be very opaque. However, it is quite standard across multiple disciplines what prefixes we use and what symbols we use for prefixes in terms of measurements. So Kent says, well, gosh, Grayson, you have almost 6,000 Kelvin there. That's pretty hot. No, 6,000 micro Kelvin. The square on that is coming from the fact that you're measuring angles over a box. Okay. Now, um, we're going to talk about the spectrum in some detail. Okay. So we're going to step through the process of exactly how the spectrum was generated, some of the math behind it, and what some of the implications are. Okay. But this is a point that I wish Grayson would have kind of pushed back on in that this is obviously just ignorance of uh, what the chart is telling you, right? And to his defense, in the moment, it's always hard, or at least harder, to just spur of the moment, have every single thing an answer ready for every single incorrect thing your opponent says. Um, but so people like me have the advantage of having watched the debate a few times and simmering on some things, but this is fundamental, right? He's criticizing the chart and he doesn't even understand the axes. It's one thing to not understand what the data itself is telling you. That's entirely forgivable. But if you're going to critique the information in the chart, at least understand what the axes are telling you, and they're not 6,000 Kelvin. Okay, these deviations, again, are on the order of hundreds to thousands of micro Kelvin. Okay, so again, less than a quarter of a percent deviation across the entire WMAP horizon, the entire sky. When we look at it with WMAP, the deviations are less than a quarter of a percent from that 2.725 Kelvin temperature. Okay, so I just wanted to make that point clear. Oh, um, and the other thing that Kent's response, he says this is the classic snow job. You just throw out a chart and you throw out data. Like that's literally what a scientific presentation or debate does. We present data and we talk about it in either tabulated or generally plot form. We generate charts and then we relate the information that the charts are talking about. The desire to just roll over it and say it doesn't matter, that I don't have to think about this. I mentioned this in the debate that Hovind had with Hugh Ross, where Hugh had a paper and Hovind said, "Oh, you have a paper that doesn't hold any weight for me." You can't debate science if you're not willing to engage with the science. Okay. And so this is another reason why I just have such a hard time stomaching Hovind. And I really wouldn't even go to make, I wouldn't take the time to make these kinds of videos specifically targeting Hovind if it weren't for the fact that he had such a large following and people thought he had good points. Um, but what I really want to point out is that those are not good points. And scientifically, when someone presents data and a graphical representation of that data, you have to engage with it. You either disprove it or at least dispute it with evidence of your own, or on some theoretical grounds, or you think about it and incorporate it into your repository, into your general base of knowledge. So, to just simply say, "Oh, this is a snow job," you're just trying to, gish gallop me with a chart, is complete and utter nonsense. Um, so, yeah. I think with that, we will actually dive into the power spectrum and how it was generated and go from there. Okay, so let's talk about the power spectrum a little bit and how it came about and what some of the implications are. Okay, so the whole idea is that everywhere WMAP looks, it has the sensitivity to find these slight temperature deviations. Okay, and it does so across the entire sky. That is going to be an important point. So if we think of the temperature fluctuations as a ratio of the local fluctuation, a single point that you're looking at in the sky with WMAP, to the overall average temperature, we would relate this as delta T. Um, However, this is prevalent across the entire sky. And so, since we see the sky as a sphere, we can write down the these temperature fluctuations across the entire sphere in terms of a set of functions that we call spherical harmonics. Okay. Now, spherical harmonics are a way of slicing up spheres into different segments effectively. Okay. And then seeing how um, those segments might behave if you have some function imprinted upon that sphere. Right. So, what we do is we expand uh, the temperature deviation function in terms of spherical harmonics. The spherical harmonics, however, require an amplitude to tell what the strength in that region you're looking at is. So we call that amplitude strength the A coefficient. Okay. Now I'll explain what these L and M numbers are for the moment, but these are basically ways of slicing up the sphere. L and M are just basically parameters that we use to slice up the sphere. The higher the numbers we get for L and M, then the smaller segments that we've sliced the sphere into, or more segments that we've sliced the sphere into. Okay. So this is the basic idea that if you have a function over a sphere, you can simply write it as a summation of these amplitudes for each individual L and M combination, and each L and M combination have a very specific spherical harmonic function, YLM, that goes with it. We aren't going to write these functions down. It's fairly complex. And I don't want to bore you too much with the math, but I do want to show you where this power spectrum comes from. Okay, this is the whole idea. So these L and M numbers are basically ways of kind of slicing up the sphere. So you imagine you have a sphere, and let's just say I want to slice it some way. I can, slice it like this, or I can slice it like this, and I can create two hemispheres. Now, without a defined pole, that really is meaningless. It doesn't matter if I slice it this way and I pull, my two spheres apart, or if I slice it this way and I pull my two spheres apart this way. Any way I orient them, I'm still just going to have two hemispheres. Okay. So L is just the number of ways that we slice our sphere. Okay, so L equals 0 means no slices whatsoever. You have a uniform sphere. L equals 1 means that I slice it in some way, and then I have um, a pole on this side and I have a pole on this side. So in this graphical representation, the slice would be like this, and you're looking at one hemisphere in the blue and then the other hemisphere in the red, but it's overlapping since you're kind of looking at it. Um, this would be like the sphere being sliced like this, if you will. So when you pull your spheres apart, you see some of the hemisphere over here and the end on this side also being pulled away, even though they're part of the same piece. L equals 2 is when I have two orthogonal slices. L equals 3 would be 3 orthogonal slices. L equals 4 would be 4 orthogonal slices. Now, so far, these slices in this depiction are just polar slices like this, right? The M's become very important in that M tells you how many actual polar slices you have. So your L numbers are just the number of ways that you're slicing your sphere. M is your polar definition. Okay. So in all of these depictions, we have L equals 4 or 4 individual slices. And the M number tells us how many of those are going to be quote unquote longitudinal. So once you have an M number in your spherical harmonic, now you have a defined pole. So M equals 0 means if I have L equals 4 and M equals 0, means that I have 4 slices for my sphere, but none of them are longitudinal. So these would be 4 latitudinal slices. M equals 1 means that I have 1, 2, 3 latitudinal slices, and I have 1 longitudinal slice. M equals 2 with L equals 4 means I have 2 latitudinal slices and I have 2 longitudinal slices. Okay. M equals 3 means I have 1 latitudinal slice and 3 longitudinal slices. M equals 4 means I have no latitudinal slices and only longitudinal slices. Okay. So the higher these numbers go, obviously the smaller each individual segment has been sliced into. Now, the way spherical harmonic theory works is that L can go from 0 to infinity, and M can only go from negative L to L. So whatever value of L you have, you can only go from negative L to L. We typically um, only consider the positive values of M because a negative M is basically like just shifting the sphere by 180 degrees. Um, we'll talk a little bit more about that in just a moment, but the way that you slice these spheres up is important. All right. Um, and I guess before going on to the next slide, let's reiterate that your L's can go up to infinity. So you can have really, really, really high L's. So a really, really, really high number of L, like say, 300, L 300, means that you sliced your sphere up into 300 pieces. And then whatever M value you have means that's the number of longitudinal ways that it's been sliced. So you can get a really complicated grid the higher up in L that you go. So spherical harmonic theory demands that the way and really it's not spherical harmonic theory, it's the mathematical theory of expansions, really demands that the way to calculate the amplitudes of each LM combination comes from this equation. Now we're not going to solve this equation explicitly, but what you do is you multiply both sides of the equation by the complex conjugate of your spherical harmonic. That's what this YLM star means. So this is your complex conjugate. And you multiply that by the value of your function that you're defining over your sphere, in this case, our temperature deviations. And then you integrate that over your entire two sphere. And in this case, sine theta d theta is the longitudinal line that slices your sphere in half. So when I integrate that from 0 to pi, I get a line that goes from one pole to the other. And then d theta from 0 to 2 pi stretches that in a circle all the way around into your sphere. So the way I like to think of it is your phi variable goes from 0 to pi, and we define 0 to be your north pole and pi to be your south pole. So you create an arc from 0 to pi, and then you stretch that arc 360 degrees out, and it fans out into a sphere. So when you integrate over that, you can calculate the value of these amplitudes that correlate with um, each spherical harmonic value. A power spectrum is basically a way of saying how strong a signal is. Okay, that's really all that a power spectrum is. The way that we typically do it is depending on exactly what kind of power spectrum you're looking at. In my field of variable stars, pulsating stars, we're looking at frequencies. So we see how the power of a pulsation, a sine wave associated with a specific pulsation, at what frequency we look at the amplitude of the sine wave that's associated with that pulsation, and we square it. And then we say that's the power that's associated with that frequency. Okay. So a power spectrum, the power is basically proportional to the square of your amplitudes. So the way that we want to generate a power spectrum is to calculate these individual amplitudes, and then we want to square them once we have them. All right. Now, in this case, we're going to do something a little bit more sophisticated in that because your M values can go from negative L to L, we want to average those negative values out. And so that's what this is going to do. Okay, so we take a term 1 over 2L plus L, or 1 over, oh man, that should be plus 1. Um, let me double check that. Is it plus? I think it should be plus 1. Let's double check this here. Yeah, 2L plus 1. That should be 1. Okay, so this is basically a normalization factor that allows all of your um, square of your amplitudes to add up to some specific value. Typically in quantum mechanics, when we normalize things, we want all of the probabilities to add up to 1. But so this is just a normalization value, and then we're going to average these square of these amplitudes, sum them from negative L to L to take into account those negative M values. Okay. When you do all that, the total power for each L that you want to plug into your expansion is then given by L times L plus 1 times the CL coefficients divided by 2 pi. All right. Again, we're not going to go into the theory of where this comes from, but just realizing that this is the expression for the power, which contains these square of your amplitudes, which your power is proportional to the square of your amplitudes. So the square of your amplitudes are wrapped up in this CL term as defined right here. Okay. So the basic idea is this. You plug in a given value of L into this equation. Okay. You plug in a given value of L into this equation, and then you plug in each value of M for that L, and then that allows you to calculate the sum of all those for each individual L, right? Because you might have L equals 5. Let's just say L equals 5. L equals 5, you would have L equals 5, M equals negative 5, L equals 5, M equals negative 4, L equals 5, M equals negative 3, all the way up to M equals 5. And so this summation says take all of those and square the amplitudes and then add those squares up. That's what the summation is telling you to do. And then divide that result by 2L plus 1, because 2L plus 1 is the number of M values that you're allowed to have for each L. Okay, so that's why this is a normalized average, right? And then when you do that, you can compute the power for each L, and it gives you, or is given by, this expression. Okay, so when you do that across the sky, this is what you get. And I can't stress this enough. This is not arbitrary. This is not just a chart that Grayson was throwing up, but it is very, very carefully measured across the entire sky, very carefully with, we're talking about um, micro deviations, micro Kelvin deviations in the um, microwave background, right? Thousands of micro Kelvin. And so when you perform this calculation for each L, again, each L makes the square of sky you're looking at smaller and smaller and smaller. So it turns out as you increase in L, you get smaller and smaller angular regions across the sky. And it turns out that right around 200 is when you get about a degree. Okay, right around 200 in L is when you get about 1 degree by 1 degree across the sky. For context, the moon is about half a degree by half a degree. So you're talking about a box that's about 4 full moons. Okay, so when you chop the sky up down into the L equals 200 range, then you're approaching a degree by a degree. When you get up into the L equals 300, or 800 range, now you're at about a fifth of a degree. All right. But the point is that the power measured in terms of the temperature deviations has a very specific shape. And the black line, well, so the black dots are your WMAP data. The black line is the fit from cosmological parameters. Okay, so basically the idea being, when you look at certain cosmological parameters, you should be able to recreate this as a prediction. And then you fit or adjust your cosmological parameters until you find the best fit. And ideally, what this means is, if the WMAP data is correct, then you can use that to measure what those cosmological parameters are. If you have an independent method to measure those cosmological parameters, you can then use those cosmological parameters to produce a predicted spectrum and see how it matches the observed spectrum from WMAP. So you can go either way depending on what information you have available. But the bottom line is that there is a process by which you can adjust the parameters in the cosmological models to fit the power spectrum exceedingly well with exceeding accuracy, right? And so the gray shaded region is the 1 sigma error region with the black dots. Okay, so there's a lot of uncertainty down here, and we'll explain why that is in just a moment. But one of the striking things is that this is non-arbitrary. Okay, so you're talking about a model, a cosmological model with parameters that you can fit, like the age of the universe and so on, and come up with a spectrum shaped exactly like this. The chances that this is coincidence are minuscule. Okay, the chances that you can have a model with free adjustable parameters that just so happens to fit the general shape of what we observe on the sky is absurdly small. That by chance, it is just astoundingly small. And this is a point that I want to hopefully really drive home. This is not an accident, okay? When you have a model with adjustable parameters, you can often come up with wildly different scenarios for your predictions. Okay, you can come up with arbitrary shapes. This is very non-arbitrary. This is extremely specific, and the fact that adjusting your parameters correctly, or at least adjusting your parameters to the point where they agree with the data, turns into this level of agreement is astounding. Okay, it is absolutely astounding. So we look at the sky, we look at different smaller and smaller and smaller angular portions across the sky, and we're actually able to see different epochs of the universe from this. And I'll explain what that means here in just a moment. But on top of that, we're able to measure cosmological parameters like the density of dark energy, the density of dark matter, the age of the universe, and so forth. All of these would be input parameters into the model. And we're able to measure it with absolutely stunning accuracy. Now, there are some deviations. We've got some points out here, and we have this data point here. So there are some deviations. It's not a perfect fit, but no data is. But you'll also notice that the error bar out here still at least hits the theoretical trend line. Now, the error bars on these data points are too small to be seen, so this data point actually is a true outlier. We actually do have some explaining to do with these points out here, but that's not enough to overturn the striking, agreement that it has overall with the theory. If, in other words, what I'm saying is, if the Big Bang were not correct, there would be such a minuscule chance that our theory from parameters and our observations of the cosmic microwave background matching in this way, the chances would be nearly non-existent. It's less than, people winning the Powerball. It would definitely be less than several hundred million. And so, when you're at that level of confidence, the only thing to say is that this is likely true. Okay. Um, Again, we cannot say that it's definitively true, but it is much more than likely true. So, some important points about the spectrum. Um, the spectrum actually represents ways that physical, mechanical waves or sound waves, acoustic waves, traveled through the universe. It doesn't have to necessarily be the early universe, but traveled through the universe. So what's interesting, this is probably the most interesting point about this peak at 1 degree represents the size of the cosmic horizon at the time of recombination. This is when the electrons and the protons bonded into hydrogen, or multiple protons bonded into helium, and your photons have a free mean path through the universe. This is the point of the origin of the cosmic microwave background. And the model, the black line, the model exactly predicts when this should occur on the power spectrum. At what point in the sky of drawing, into subsequently smaller and smaller and smaller boxes, should we really see the imprint of that recombination on the sky, and it matches our observations perfectly. For the fluctuations for L less than 50, right? So if we come back here, um, so in this region right here, these fluctuations are due to inflation itself, okay? And you'll notice more or less they're relatively flat, and there's a slight parabolic shape perhaps, but it's relatively flat compared to the amount of deviation that we have up here, right? So if you look at the amount of deviation from L equals 0 to L equals 50, we're talking um, a few hundredths or maybe I should say maybe a few hundreds um, of microkelvin deviation, whereas again the peak is almost 6,000 microkelvins deviation. So a few hundreds of microkelvin deviation compared to 6,000. This portion is relatively flat compared to this portion. Okay, and on top of that, the inflation predicts that the um, deviations should be Gaussian. So what that means is just a bell curve. Some of the deviations are going to be very small. Some of them are going to be very large, but you have an overall average for which the deviations occur. And again, it should be relatively flat. For your very high L's, your spectrum should decay exponentially. And this is what we see over here, okay? An exponential decay down. And again, the uh, Big Bang model with the adjustable parameters predicts that you see these two spikes and then your very rapid exponential decay down here, okay? So, in short, the spectrum is basically communicating information about different epochs of the universe: inflation, recombination, and then our current universe. Okay. And this is why I said earlier that inflation actually has some evidence for it. The evidence is imprinted in this power spectrum, right? Based on what the classic model of inflation says should happen in the early universe, it more or less is happening right here. The deviations are fairly flat. You have some that are close, you have some that are far. That will follow a Gaussian bell curve. And then once recombination happens, you should see larger and larger deviations until they peak at about the 6,000 um, microkelvin, or about 0.006 Kelvin, if you will, scale. And so, once again, I have to stress these deviations are minuscule. We're literally measuring, you know, less than a quarter of a percent deviation, which is incredibly small, right? Um, and so, with that being said, where does the Big Bang stand today, right? What caused inflation? We don't know. Where are the magnetic monopoles? Well, inflation may have taken care of them, but it's still a puzzle why we don't see them. Um, it took care of their density. In other words, it would be very rare that we should see them, but they should still be out there, right? Another current puzzle is where is all the antimatter? This is not a prediction from the Big Bang itself. This is a prediction that comes from atomic theory and from particle theory. But at the energies that the Big Bang possessed in the early universe, any particles that came into existence, like electrons, should have had a antimatter counterpart, a positron, um, associated with them. So where is all the antimatter? This is a big puzzle. We really don't know. And the active area of research is called CPT violation, charge parity time violation. Um, and it really is a puzzle. We are not sure where all the antimatter is. What are dark matter and dark energy? We really don't know. We have really good evidence that they exist, uh, but we really don't know. One thing I've glossed over in this presentation is that in 1998, um, a couple of folks observed the universe to be accelerating. So the Hubble law predicts that the Hubble law by itself predicts that the universe has always been expanding at a constant rate. But the measurements in 1998 seem to indicate that the universe was expanding faster and faster and faster. So the rate at which the universe is expanding seems to be increasing and is not constant. Um, my understanding is that the most recent Observations from JWST might be throwing that into doubt. Do not quote me on that. I will look and I will make an updated addendum to this video. Um, but this was going to be long enough anyway that I didn't really want to get into um, those details. But it is worth mentioning that dark energy is the acceleration of the universe. Okay, the acceleration of the rate of expansion of the universe. And ideally, we would like to know what caused the universe, but at this time, it's beyond what science can probe. Right? It is a valid question. It is a great question. What caused the universe to come into existence? But scientifically, we don't know. So Kent, of course, wants to take that as a you know um, touche against the Big Bang Theory and say that because we don't know where the energy came from, we don't know where space, time, and matter came from, therefore we don't have a complete theory. In his words, we haven't gotten off of first base. It's just entirely inaccurate. We don't measure scientific theories that way. They don't have to be complete in order to be good theories. The Big Bang Theory started from a basic assumption from equations, Einstein's equations, and said, assuming Einstein's equations are correct, what are the implications? And the implications seemed to be an expanding universe, complete with a prediction of Hubble's law, confirmed by Hubble, complete with a prediction of a black body radiation bathing the universe in the microwave region of the electromagnetic spectrum. We found that. This temperature prediction was slightly off. I'll talk about that more here in a moment. Um, but overall, the predictions have been confirmed. The ratio of the hydrogen to helium in the early universe, 75 to 25, has been confirmed to stunning accuracy when we look at the oldest stars. Um, and so I will also say there is a puzzle that I didn't put here that's worth mentioning. On the point of early nuclear ratios, while the hydrogen and helium seem to be confirmed with really, really good precision, even though the lithium seems to only have, predict trace amounts, the trace amounts that were predicted do not match observation. So that's another area where we have an open puzzle with the Big Bang Theory. Okay, so I did want to mention that. It, to my knowledge, has not been solved yet, and I don't even know if we have any good um, uh, progress being made on that front just yet. Um, so there are puzzles remaining, and once again, it's worth reiterating that this is a theory. It is not something that we say, has been proven beyond all shadow of a doubt, although the evidence is fairly overwhelming at this point. The existence of the power spectrum itself, the fact, oops, the fact that we could predict the power spectrum and that we could predict the points where the power spectrum, peaks is incredible. It's non-arbitrary physics, and therefore, it just can't be taken as anything other than confirmation of the Big Bang Theory. Again, we don't say that it's proven true, but it definitely serves to affirm the Big Bang. Um, so, with that, I will make one more small statement about the prediction between, or the agreement between the prediction of the temperature and the actual measurement of the temperature, right? So, if we come back up here, right? So, uh, it was initially predicted that the Big Bang was, or not the Big Bang, but the cosmic microwave background would produce a temperature of 5 degrees. right? When we measured the cosmic microwave background, it would be 5 degrees. It was measured to be 2.725. And some people would look at that and go, aha, a failed prediction. So, what I want to do with these next few minutes is talk about the difference in the levels of confidence of predictions, right? And why sometimes, even though if a prediction does not match observation perfectly, we still count it as a successful prediction. And in other cases, we do not. Okay. So the it has to be stressed here. The Big Bang predicted that the radiation would follow a black body spectrum. This is exactly what we found from both COBE and WMAP. That is a very specific prediction. Okay. Once you understand some physics, it makes sense that it should be black body, but arbitrarily it didn't have to be. So claiming that the radiation would be black body is an extremely specific prediction. And the temperature estimate basically came from the age that we thought the universe was at the time, that Alpher and Herman thought the universe was at the time. So they said, okay, it would be roughly 5 degrees. There's a humorous quip that Neil deGrasse Tyson likes to cite, um, and he says the physicist Richard J. Gott uh, tells this story that he says this would be equivalent to predicting that a 50-foot flying saucer would land on the White House, but instead a 27-foot flying saucer shows up. Right, 5 degrees Kelvin, 2.7 is what's measured. Complaining about the discrepancy between 5 and 2.7 in this particular instance is like complaining, well, gosh, they said this flying saucer would be 27 feet instead of 50, right? The fact that the flying saucer showed up at all is so non arbitrary that if that happened in real life, somebody said, a flying saucer of about 50 feet is going to show up and land on the White House lawn at some point in time. And then a flying saucer of 27 feet shows up. Okay. Very few people in that moment are actually going to go, that doesn't look like it's quite 50 feet. I think you were full of crap. Okay. Most people are going to go, how did you know a flying saucer is going to land on the White House at this time? That's what they're going to be concerned with. That's the way we view this prediction. This is such a specific prediction. The fact that it is black body radiation is such a specific prediction that the fact that it's 2.7 Kelvin instead of 5 is kind of an afterthought. Okay, and I'll explain why here in just a minute, but it's kind of an afterthought. It really is akin to how did you know the spaceship was going to land? Right. So, why is this not thought of as a failed prediction? Because the methodology used to come up with the 5 degrees was using incomplete information. So as we were able to fill in that information better, using their same methodology but updated parameters for the age of the universe and the density of dark matter and dark energy and so on, we can now use their same methodology with those updated parameters to actually now retroactively predict 2.75. And you can say, but it's a retroactive prediction. You're not supposed to be able to do that. You can make retroactive predictions in science we do it all the time. And we also do it to refine models. There's nothing wrong with it. It's just not quite as novel as the original prediction. But when you use the same prediction methodology, just with better updated parameters, and you get the better the value that agrees with your observed values better, there's nothing wrong with that. It's actually good science. It actually allows you to say something or some things interesting about your model. And the fact that using more updated information allow from other areas of the model, the age of the universe and so forth, allows you to confirm a very careful measurement to stunning precision actually only strengthens your model. It's like taking things from this over here and using them to build something over here that it's incredibly strong. So it is not a failed prediction in that sense, um, even though it's almost a factor of two off, right? It's almost a factor of two off. It's almost 50% off, or 100% off, 200% off, depending on how you do your percentages. Um, so contrast that with, for example, the Bohr theory of hydrogen. When Niels Bohr was developing his theory of hydrogen, he was able to retroactively predict where the spectral features in the hydrogen spectrum ought to be, the emission lines, right? So your H alpha line, your H gamma line, your H beta line, and so on and so forth. He was able to say where each of those should be in the electromagnetic spectrum. If he had been off because those values in the laboratory were known to such high precision, and we viewed the same spectral lines every single time we did an emission spectrum with hydrogen in the lab, if his predictions had been off by 5%, it would have been absolutely detrimental to his theory. But it was because the spectral lines were so well known from the lab. The age of the universe was not very well known. The dark energy hadn't even been discovered yet. Dark matter was being debated at the time. So the fact that this prediction didn't exactly match the observed value, the 5K prediction didn't exactly match the 2.7K observation, is in no way, shape, or form a debit against the theory. It's actually a credit because it was a prediction that turned out to have validity to it at all. It turned out to be a black body spectrum. It happened to fall in the microwave background. And once we were able to update the age of the universe to better precision from other methods using WMAP data and the Friedman equation, we were then able to come back and exactly say what this spectrum should look like and exactly what temperature it should have. So that is why we do not take the prediction of the temperature and the observation of the temperature to really be disparate, but actually be a confirmation of one another. Okay, so that is a short overview of the Big Bang and where we stand today. Um, I hope you found this video helpful. And if any of my videos ever make their way to Kent, honestly, I'm not sure I'd be interested in doing a debate just because of the way he gish gallops. If he were interested in an honest discussion, I can say that I think I would take him up. But given that he has been in these debates hundreds of times, he's been corrected on his methodology and thinking hundreds of times by PhD experts, by science communicator experts, by experts in their respective fields. At this point, he's just being um, the only options are he really is that dumb or he is a grifter. And my money is on the grifter for various reasons. I don't necessarily like to, take part in any sort of ad hominem attacks, but it's not necessarily ad hominem to call a grifter if they really are a grifter. So um, I'll leave that at that. But if you enjoyed this video, give it a thumbs up, give it a like, and we will see you next time.